Uh, Hi everybody, and welcome to the last day of the workshop. We're very excited to have Moritz Hardt, the director of the Max Planck Institute for Intelligent Systems, giving a talk to us today. I think really somehow being the organizer for this workshop, it feels like I'm announcing the Avengers. We have really quite the assembly of like top researchers in this area. But really, this list will not be complete without Moritz. Moritz is someone who has been working very actively to somehow redefine the way we think about computation and intelligent systems from the perspective of social science and society, and introducing a new powerful concept like performative predictions and many other ideas that we've already been seeing in this workshop. And we're very, very excited to have him and even happier to have him in person. Thank you so much, Moritz. Please.
Yeah, thanks so much, Jorgis. Really appreciate it. Pleasure to be here and see so many of you in person. I'm going to be talking about the invisible hand of prediction, which is a title that'll make increasingly more or less sense as I go along in this talk. So you'll see. This is based on joint works with Mina Jagadisan. I got that right this time. Celestine Mendler-Dörner, Juan Carlos Perdomo, and Tiana Jernick. And three of them are in the audience. So I'll still practice. Okay, so 3 out of 4, it's strong for me. Okay, so yeah, so okay, 3 of them are in the audience, and we'll be able to correct any mistakes I make. So that's good. So the starting point for my talk is the observation that a whole lot of the discussions we're having today, the debates about algorithms, are about sort of the causal effects of algorithmic predictions. Okay, so we're interested in things like how recommendations and ads shape preferences and consumptions, how selection rules incentivize individuals to adapt to either through gaming or manipulation or self-improvement, various mechanisms. We heard a lot about forecasts in this workshop, and they can influence obviously behavior and interventions. And then there are risk scores deployed in consequential settings in this country and elsewhere that change life trajectories, sometimes drastically. So all of these are examples of causal effects of algorithmic predictions, right? Things where like predictions that we make have some kind of downstream implications. And so this talk is about how predictions steer populations, how they change populations, and how these are often sort of invisible causal forces that lead to changes in a population given the predictions that we make. I'm going to introduce or recap a framework for reasoning about such predictions, effectual predictions, and that's called performative prediction. Okay, and it's a general conceptual framework to reason about these things that we developed here a couple of years ago. And I'll tell you and review some emerging results and relationships to another area that some of you have worked in, including myself, called strategic classification. Okay, and then I'll transition into a new observation that we call performative power. And that's like a new tool, a conceptual tool that's sort of derived from performative prediction for measuring power, market power in digital economies. And I'll explain why I think this is sort of a useful complement to classical antitrust machinery and why it brings something to the table that I think classical tools don't necessarily have or struggle with, okay? So let's start with the basics. How do we make predictions? You all know this. We represent a population of individuals as a fixed distribution D over data, typically features X and an outcome variable Y that we're trying to predict from X. And our goal is to find a predictor, theta X, that minimizes some loss function on this distribution D, okay? And this leads to this notion of risk that we're trying to minimize, risk minimization. So risk is of a predictor theta on a distribution D is just the expected loss of theta X on Y for random draw XY from the distribution, okay? This is risk. We're typically trying to minimize that. I'm not going to talk about how, but you're all aware of many tools in supervised learning that minimize risk, okay? What I draw your attention to instead is the fact, somewhat implicit in the setup, that the prediction cannot influence the outcome variable, okay? And this is sort of kind of obvious, but it's because you sample X and Y at the same time, okay? So Y is determined when X is determined. There's no chance that anything derived from X can influence Y because you imagine that you had sampled them at the same time, okay? So, supervised learning is never, is always sort of static, right? In the sense that the outcome cannot be influenced by anything you do with the features. Okay, in other words, in particular, we ignore the causal effects of prediction. It's a little bit funny that all the issues we have with prediction are sort of about the causal effects of prediction, but the main way we reason about prediction, supervised learning, is ignoring that. It doesn't have a way of coping with that. Okay, so recognizing this issue, and this happened like a long time ago, this reckoning, and especially economics and finance in the 70s, but failure to take into account causal effects of predictions is dangerous. It leads to all sorts of problems in policy and forecasting. Often goes by Goodhart's law, who stated this in the context of financial policy, that if you actually use predictors or statistical regularities to make policy, you try to control, you try to steer using statistics, these patterns that you were trying to use often disappear, okay? This is also closely related to Lucas' critique in the context of macroeconomics, who observed that, macroeconomic policy making or policy, problems can disrupt the statistics that motivated policy, okay? So recognizing these issues, we propose performative prediction as a way to extend supervised learning just enough to be aware of the causal predictions of the predictor. And so the way this works is we introduce the notion of performativity, or it's actually not a new notion, but we introduced it in the context of supervised learning. And we postulate that upon deploying a model theta, so when a firm or institution deploys a model theta, the population changes in response to that model from the original distribution D to a new distribution D theta, okay? So D theta is what we call the distribution map, and the distribution is allowed to depend on the model that was deployed, okay? And the idea of this D theta, distribution D theta, is that it captures kind of the aggregate macro level change to decision rule. Okay, so it's the population change, the population level change resulting from a decision rule. And of course, there's some modeling involved here. You need to fix a time horizon and so on. But conceptually, it's the change that results from the deployed model. And so this leads to this extension of risk called performative risk, where you evaluate a predictor theta on this distribution D theta that now depends on theta itself. So it's a bit of a moving target problem. So you draw a sample from xy from this distribution D theta, and you look at the loss of theta x on y. And now here, importantly, in this expectation, that is with respect to the distribution D theta. Okay, Raf.
So x and y are still drawn at the same time, just from D theta.
Just from D theta, yeah. But you see, basically, the distribution had a chance to depend not just on theta x, but on the whole model theta, right? So in particular, it could have, already like, it could already depend on, the y could depend on theta x, right? Because the distribution D theta depends on theta and all its prediction that it makes, you can make it such that y depends on theta x. That's an important point. So it does have that dependency. You can create that, okay? So you can easily model things where y depends on theta x. So for instance, y could be a biased coin toss with, biased theta x. Right? That would be easy to express as abstractly as such a distribution. Good question. Okay, and so just as a note to get you thinking about this, in practice, performativity often shows up as some kind of distribution shift after deploying. Okay, so your recommender system, you ship a new model, it starts making new recommendations, people watch different things, and you're like, oh, the distribution has shifted, right? But of course, that's a sign of performativity. Okay, your predictions are changing the world and they're changing consumption. Okay, so there are two different solution concepts that this leads to once you introduce the simple change. The first one is optimality or performative optimality, and the second one is stability. So let me start with the first. So a model theta star is performatively optimal if it minimizes the performative risk. Okay, so it's just a minimizer of the performative risk. Okay, that's all that says. That's pretty straightforward. But it's a complicated objective because it's sort of moving target thing. You're trying to be good on the distribution that your model entails. Okay, so this is what performative optimality says. Okay, and so contrast this with a slightly different condition of stability, where we say that a model theta star is performatively stable if theta star minimizes risk while holding the distribution fixed that results from it. Okay. So you just hold the distribution fixed that results from your model, and you sort of minimize one more time. Okay, you cost some distribution to manifest, and now you minimize and you see what happens, okay? And so a stable point is a fixed point of risk minimization, okay? So you're in some distribution, you minimize risk. If you don't change, if you get the model that you already had, then you have a stable point, okay? So stable point is a fixed point of risk minimization. If you have a stable point, you do risk minimization, you don't change. You stay at the same model, or at least at something that's equivalent to your model has the same risk, okay? So stable points, the best way to think about them is operationally. Your recommender system, if you train and your loss doesn't go down or doesn't change, then you have a stable point, okay? Here's another way to think about this that will be particularly relevant for this talk. I'm going to think of, this kind of performative optimality as a notion of ex post optimality. Okay, so you successfully steered the population towards a state that is beneficial to you. Okay, so you somehow managed to find a d theta on which you have low risk. So ex post, after observing the new distribution, you somehow have low risk, right? So it's a notion of ex post optimality. After the distribution manifested, you're good on that distribution. And I think of stability as a form of ex ante optimality. Okay, you sort of take the distribution for whatever it is, you hold the distribution fixed. These are just the conditions that you observe the data, and you just optimize against the conditions that you have, okay? So that you don't care about what happens after. You're just optimizing the distribution that you have, okay?
So is it correct to think that distributional robustness is just something between?
Distributional robustness is something in between. Yeah, it's a little bit different.
Neither. It is, here you're fixing it, here you're changing everything. You can take a ball and then say that I minimize over that.
Right. So you could do something like, you have to express it as a distribution. So let's say you try to express an infinity ball. You do something like you sort of, uniform over an infinity ball or something like that. You can probably like relate this to notions like that. Yeah.
I thought you motivated this earlier by saying that the distribution would change in response to the choice of theta.
Yeah.
I feel like the equilibrium or the stability should be with respect to a potentially changing distribution. I'm a little lost on.
I see. Basically, yeah, if you think of this as an equilibrium solution, it's sort of a one-sided notion, right? Like if you did one more step of risk minimization, you wouldn't move. You're in a stable state, right? You could imagine swapping the arguments that would give you a different equilibrium solution. Maybe this is what you're getting at. You could, if you think about it as a two-player game between the distribution and the classifier, right? Then this is sort of just a one-sided equilibrium in that game where it's stable with respect to the classifier. It need not be stable with respect to the distribution. I think this is kind of what you're getting at. And I think you have a two-player game in mind where this is not like a Nash equilibrium, right? This is not like simultaneously. This is not an equilibrium when they're simultaneously.
Although if d theta is like the best response of the distribution to theta,
Then you get it. Yeah, that's right. Yeah. So hold that thought. That's going to be relevant later. If you know more about what d theta is, then you get like an equilibrium notion we're familiar with. Okay. So that's going to come up in a second. So maybe like hold that thought for a second. And but yeah, I mean, for now, just think of it as like a one-sided equilibrium with respect to the classifier. Okay. That's what I call stable state. Okay, so on this like notion of like ex post optimality and steering versus ex ante optimality and optimizing, there's like a nice way to conceptualize this optimizing versus steering that I think is very fundamental to performative prediction. Suppose we're in a world given by a baseline state theta 0. That's like maybe a past deployed model that the previously deployed model, and it gives us a distribution d. That is, d theta 0. So it's like the distribution d resulting from theta 0. And I can trivially write the performative risk of a predictor theta in this kind of like decomposition. So there's nothing going on here. I just write it as the risk of theta on d plus the risk of theta on d theta, performative risk minus, the risk of theta on d. Okay, everybody believes this fact, right? This is the kind of theorems I prove, okay? So, but I like these because they get you sort of thinking in the right way, okay? So here, the way you should think about this is that the first term is the ex ante risk, okay? It's how well you optimize against current conditions. Think of theta 0 as some kind of like state of the economy. Then the ex-ante risk is how well you respond to the state of the economy. Okay, that's ex-ante risk, how well you optimize in current conditions. The ex-post advantage is what I call the second term. And this is how much you can gain from steering, right? This is when I take like ex-ante optimization as a baseline and I imagine, or I look at how much better I can do by pushing the distribution into a state I want, d theta, okay? So this is kind of the ex-post advantage of this predictor theta. It's like how much does this predictor benefit from having moved the population to d theta, okay? So, and this is what I mean by this decomposition. If you want to minimize performance risk, the way to think about it is one thing you need to like respond well to like existing conditions, and the other is you need to have an ex-post advantage. Okay, this is kind of how you can think about it. Does it make sense?
I mean, it doesn't really, like you've described it as an advantage, but intuitively, would you actually think of it as like a disadvantage? Like I would expect that second term to be positive.
Yeah, it's negative, but you know, it's sort of like it's, you know, loss is something you want to minimize, so an advantage is like a negative term. Does it make sense?
Sure.
You could also write it as like minus and then some other term. There's a big family of theorems here where you change the sign. Yeah, but your observation is correct. Like it is a negative term. That's correct. And it's sort of how much you can make the loss smaller by playing around with this ex-post term d theta. That's the right way to think about it. Yeah. So keep in mind, perform risk equals ex-ante risk plus ex-post advantage, right?
So if you did the simple thing where you're just tuning theta based on like learning from D, then it wouldn't be right.
All right, can you hear the last word?
So like sometimes it could be positive, sometimes it could be negative.
Yeah, that's right. It need not be negative. Like, you know, if you're doing well, it's negative, right? But it need not be negative. Okay, and this is like, this could be positive or negative, right? This term. So, okay, just good one. All right. So the first question, you know, you might have an algorithmic question about the setting is, can we even find stable points? Okay, so this looks like a pretty terrifying objective. Can we even find stable points in generality? Okay, and so there's one way to try to do it. Since stable points are the fixed point of risk minimization, you can just repeat risk minimization. You just play out the fixed point iteration, see what happens. Okay, so that's repeated risk minimization. In practice, that's sometimes called retraining. It's sort of what a lot of practitioners do, just retrain your model every day. Does that converge? Okay, so repeated risk minimization is the following heuristic. You find a model theta that minimizes risk on the current distribution. Then you deploy the model and you observe a new distribution d theta. Okay, and you go on, repeat. Does it converge or not? This is the first sort of theorem we proved about performance prediction with Hoanki and Tiana and Celestine a couple of years ago. And the informal theorem is that if you're you have a smooth, strongly convex loss and an insensitive distribution map, in a sense that I'm going to make precise in a second, then repeated risk minimization finds a performative stable point. Okay, so you converge under some strong convexity assumption and smoothness assumptions, fairly strong, but sort of standard optimization assumptions. But strong convexity is kind of necessary. Okay, so there's something specific about strong convexity for performativity. Weak convexity is not enough. Okay, so you need strong convexity here to converge. Okay, and a little bit more detail. You need the loss function to be smooth, beta smooth, in both arguments. The loss function has two arguments. You need it to be gamma strongly convex, and the distribution map has to be epsilon sensitive. And then you get this geometric rate of convergence determined by these three parameters. And when I say epsilon sensitive of d theta, you know, what does it mean to be insensitive for a distribution map? It maps, you know, a parameter vector theta into a set of distributions, right? Into the set of distributions. So you need some kind of probability metric, okay? And the one we pick and the one that's sort of the right thing for this proof is the Wasserstein metric or Earth-Merkur distance. So we look at the Wasserstein metric between d theta and d theta prime, and you want that to be at most an epsilon times the distance and parameter vectors. That's what I mean by insensitive. So changes in your model parameters don't change the distribution arbitrarily, okay? So that's the thing you need to make this work. That sound good? Okay, the proof is relatively short, but I'm not going to go into it because the talk's kind of about something else. But I tell you that this led to a number of like nice results, you know, that use similar assumptions. So this epsilon sensitivity was very helpful in proving a number of results. The first one you saw, how retraining converges to a stable point. You extended that to stochastic optimization results. There was also a nice paper out of UW by Drusyatsky and Zhao, who had a nice generalization of this. Then John Miller, Hanke Perdomo, Tiana Jonik, had a result on how to actually find optimal points, not just stable points, under assumptions that kind of make the performative risk convex. So there are assumptions where the whole performative risk becomes convex, and then you can optimize it. So that was this paper. There have been a couple of papers, maybe more at this point, about stateful and time varying distribution shifts. So what if like you deploy a model and then your distribution changes in multiple steps, or it changes as some like function of time? Okay, there's also a lot you can do. And again, you can extend these assumptions to these kind of settings. And then also see Lillian Radliff's talk on Wednesday for a number of results on performative prediction, in particular, like an interesting setting of multiplayer performative prediction that she talked about. Okay, so there's a whole a lot of activity here that I'm very excited about. But there's still many open problems. In particular, things I don't have good answers to is what happens with over-parameterized models and performance prediction, non-convex losses, and the question that always bothered people with is sort of what's the kitchen sink approach to performative prediction? If you just were a deep learning person, I'm already being like mocked here for like stating this again. So if you thought like a deep learning person, you had all the resources in the world, how would you solve performance prediction, right? Like,
And by that you mean all the like data, all the features, all the computation, all the.
you tell me, yeah. So whatever
I'm
you
not
want
a deep
to,
learning
yeah,
person.
whatever you want to throw in the kitchen sink. Okay. So yeah, Ref.
Well, I guess I'm a little, so when you say solve the problem, are you trying to find the stable point? Because it's not clear to me that you would want a stable point necessarily. Like maybe the optimal thing to do like for the world is to have a classifier that's just slightly off from the distribution that it induces, but that's like better for everyone.
Excellent question. So Ref's asking a great question. Is like normatively as a stable point even what we want, right? Or is optimality what we want, or some other thing? And I think connecting this to like welfare or utility, I think is really important. That's another great open question. Like, how do you, what is actually good? Like, if you had some like notion of like social welfare, right? Like, what would actually be solutions that we want to have? Grant, and then Jamie.
This seems to assume that you know the model. Is that like a realistic assumption in a lot of cases, or are you kind of learning the model as you're?
What do you mean by you know the model?
But you know how the distribution is going to change in response to everything.
No, so you don't, right? So this is this part of why in this repeated risk minimization, it's in sort of an experimental iterative procedure, right? But you don't actually know what the distribution map works like. You just like deploy the model, see what happens, deploy the model, see what happens. So you don't have.
So the heuristics you're thinking of are similar to the
right. They could be in that nature where you don't have like a model for the distribution family. You just kind of keep deploying and hope that something good happens. One exception is this paper here that I mentioned that has like parametric assumptions on the distribution map or some kind of distribution family assumptions. That's also like a good question. Like, what happens if you have statistical assumptions on distribution? Yeah.
I'd like to go back to that discussion about differentiating this from the distribution shift framework right now. Like we're saying, so because theta being introduced in the world is just one of the many ways the distribution can shift, right? And so, so my question is kind of like, if you have any intuition with when is this framework more adequate to reason about your problem, in the sense that that the theta is going to be the main thing, or not just one thing that you just are ready to go.
Right. So Harman is asking an excellent question, right? So when you deploy a model, right, and you look at what happens, there's like this causal soup of like things that happen, right? There's like time that passes, weekdays, natural drift, all sorts of things, and then there's the causal effect of your model, right? So there's all sorts of stuff happening, and for this model, everything else that's happening is exogenous, and you only look at the causal effect of the model. And for this to kind of make sense, you sort of want to be in a setting where the model deployment is kind of the biggest elephant in the room. Okay, so this is kind of like the main thing that's happening. So if you look at maybe it's a small time scale, like your recommender system, you're deploying it. You're looking at 1 week, 1 week of traffic. You updated your model, and you think that mostly the distribution shift that you're seeing is due to like the new predictions that you're making. There are other settings where that's probably not the case, right? And so we'll come back to like settings where, or like how much performativity we expect there is in different settings. And that's actually going into the second part of the talk. So we'll go into that, Jamie.
Although presumably this repeated risk minimization stuff would be the thing you'd want to do even if you have a mixture, right? Because like you care about, I mean, it could be a thing you want to do, right? Because it'll deal with the exogenous stuff just fine.
Okay. Yeah, so that's another good observation. Yeah, so the repeated risk minimization is a heuristic people do anyway, right? So in some sense, this results like descriptive. It's saying like if the distribution shift happened from, were caused by your model, it would converge, right? And you can probably also throw in like extra noise terms or whatever, right? Maybe something, will still work. Yeah.
So in the theoretical result, you need new samples each time you take a step to estimate this D, or do you have this case of function?
No, so in the repeated risk minimization, you do need new samples because the distribution is new. So you kind of imagine that you collect new observations after every model deployment.
Did you mention how many samples you need?
Yeah, I mean, this is, I was talking about repeated risk minimization. So it's just like, I'm like talking about the population dynamic. And then you can relate that to finite sample either through like stochastic optimization, like you do here. You get slightly different convergence rates, or you can do like, just uniform convergence and, argue it that way. Okay, but this is sort of, these are the two options you have. All right, let me go ahead, and I'm excited about the interest here, and should look at all these papers and think about this. There's kind of an important transition I want to make, which is moving from this macroscopic perspective about like population aggregate level changes to more of a micro perspective. And so I said that performed predictions about these population dynamics, and most positive results are finding stable points. But from this like aggregate perspective, it seems to be pretty hard to kind of find optimal points. Okay, it's kind of delicate, and if you think about these population dynamics, a difficult thing to do. Okay, and so is there perhaps like a micro perspective by which you sort of make stronger assumptions about where this distribution shift is coming from that give you in result, in turn like better or stronger results? Okay, and the answer is yes, and we'll see that. And in fact, many of you are already familiar with it because this is the setting of strategic classification, where you assume that the distribution shift d theta comes from strategic behavior of individuals trying to adapt to the decision rule. Okay, so in like performance prediction, you didn't have this interpretation. It could be anything, right? But here in strategic classification, you assume that there's some kind of individual that strategizes against your decision rule and changes their features as a result, of your predictor. Okay, and when you go down this route, it makes sense to pick sort of the standard econ assumptions, or what I call standard microfoundations, which is that you assume a rational utility maximizing agent. You assume that the agent is sort of representative for the whole population, and you assume that the agent computes the best response to the decision rule. Okay, so these are kind of the standard assumptions that game theorists or algorithmic game theorists like to throw in when we model individual behavior. Okay, so we've all kind of gotten used to these assumptions. And this is also the route we took in a paper several years ago. It's Nimrod Megiddo, Christopher Paparizio, and Mary Wooters, where we introduced the strategic classification model, and there's been a lot of work. And so the advantages of these standard microfoundations are kind of clear. It gives you like a precise characterization of the distribution map. You now know analytically kind of like what happens when you deploy a classifier. And as a result, because of this kind of analytical control that you have now, there are many ways to find performative optima. And in the setting, they're called Stackelberg equilibria. Okay, so like your classifier is optimal with respect to the best response of the agent. That's a Stackelberg equilibrium. And there's been all sorts of work, varying cost functions, model families, approximate best response, multiple different cost functions, online setting, and so on. And all of these give you positive results. Okay, so there's actually a lot you can do with these assumptions. And I think we understand relatively well now, like all the things you can derive in strategic classification from these standard assumptions. Okay, so the thing I want you to keep in mind is that strategic classification is performative prediction plus standard microfoundations. It's what happens when you instantiate this general setup with the standard assumptions, the standard AGT assumptions about sort of user behavior or like agent behavior. Okay, in a recent paper, we sort of pointed out some issues with these standard microfoundations in the context of strategic classification. So this is work with Celestine Lerner and Mina Jagadisan. So the first observation is that, this aggregate response, d theta, that you get in strategic classification necessarily has discontinuities that you don't necessarily observe in empirical settings. So basically the way this always works is if you have some kind of threshold rule and you have some budget that agents have, some kind of cost they're willing to incur, then everyone who's within the cost of the threshold will move up to the threshold and exactly to the threshold, and everyone else will stay put. So a d theta in the setting would always look like this, right? And that's obviously not something you see that often. I'll give you a few examples. One where you kind of see it, but most of the time you don't see this sort of thing. The second thing that's kind of concerning about these assumptions is that any positive fraction of non-strategic agents destroys the existence of stable points. Okay, so the moment some people choose not to strategize or don't have the ability to strategize, you lose these kind of nice properties. And third, these standard assumptions lead to something that lead to solutions that maximize a negative externality called social burden. So in some sense, they're most beneficial for the decision maker and least beneficial for the individual. Okay, so basically the price that positive instances have to pay to be accepted is maximized by these kind of assumptions. So they're maximally sort of, welfare minimizing, right? They're like best for the institution, but they're extremely conservative. And as a result, they maximize this burden on the individual. Okay, I'll skip over the examples. Again, this is with Mina and Celestine. I'll skip over the examples where this happened. You can look at this paper. And instead, I want to move into the second part of the talk. There's been a lot of discussion, so I need to move on. So what's, let's recap on performativity, right? So I hope I convinced you that once you know this concept, you sort of see it everywhere, right? You can look at your favorite prediction problem in the social world, and it's probably performative, okay? And so if you're like me, you can even box yourself into the corner where you would say with a straight face that any social prediction problem is performative, okay? So I would make this claim. And if you find like a prediction problem in the social world that is not performative, let me know, okay? And so we saw that performative prediction is sort of, fundamentally, it's about this difference between learning and steering. Learning from a population versus steering a population, okay? And so remember, performative risk equals ex ante risk, which I interpret as learning or optimization, plus ex post advantage, which I interpret as steering, okay? So this is where the invisible hand of prediction comes in, okay? So if social prediction is necessarily performative, as I would argue, the question is still how much, okay? And this is also, we touched on this, like how performative are the predictions that we make, right? If I make predictions as a professor in my office and nobody listens, right? It's probably not very performative, okay? If I'm, the central bank of some government and I make like, inflation forecasts, probably highly performative, right? If I'm the only traffic routing app around, I'm probably highly performative. And if I like change traffic predictions for people, they probably go a different route, okay? So you think about this and you work out all these examples where things are performative, and you notice that the strength of performativity, intuitively speaking, depends on power, okay? It depends on the power of the institution or the firm or the individual that makes the prediction, okay?
Is there a distinction in prediction and like classification or decision that's being made here? Because I thought we were talking about decisions before, but now we're talking about predictions, and maybe we're talking about predictions the whole time.
So yeah, the question is, are we talking about predictions or decisions? So in the formal model, there are two answers to this, right? In the formal model, the causal power comes from your model, right? It's like the distribution depends on theta, and it's allowed to depend anything about theta, including decisions that you make based on data or predictions that you make. It could be a probability number that you write on some website. It could be like a hard decision that you make, right? So the setup generally accommodates like anything that you do based on your model, okay? So it includes these things. But yeah, I mean, I think it's closer, intuitively speaking, to a decision because you kind of wanted to have some causal powers, right? So, and it shouldn't surprise you with the benefit of hindsight that somehow performativity is related to power, because like one dictionary definition of power is literally the capacity or ability to direct or influence the behavior of others or the course of events, okay? So it's not surprising that performance prediction is somehow related to power. And so then you can turn this logic on its head and you can ask, can we use performativity to actually reason about power, to actually reason about the power of predictive systems, okay? And so in particular, I want to get you thinking about this kind of question: when does a digital platform have too much power or have monopoly powers, right? The sort of typical question you ask in antitrust regulation. What does it mean for one of these algorithmic platforms to have too much power, right? Like YouTube or Facebook and so on. And so digital platforms are tricky for current antitrust frameworks. And it's kind of interesting, just in recent years, there were two major reports that really drove home that point. The first one is by the Stigler Committee on Digital Platforms. I think Jamie was involved in that as one of the experts on the computer science side. And there are many quotes that make this point, but one of them is pinpointing the locus of competition can also be challenging because the markets are multi-sided and often ones with which economists and lawyers have little experience. This complexity can make market definition another hurdle to effective enforcement, right? So market definition is an issue here because like somehow these platforms don't operate within like classically recognized sort of market boundaries, right? It's like very hard to define like what kind of market they're actually operating in. Is it the advertising market or the media market or the news market or whatever, right? So what is the kind of market definition you would even apply to these things? And there was a sort of counterpart to this report by the European Commission, which had similar conclusions. It argued that there should be less emphasis on analysis of market definition and more emphasis on theories of harm and identification of anti-competitive strategies. So it said like maybe we should like, forget like about these market-based or market definition-based frameworks and think more about how we actually measure anti-competitive patterns, okay? And this is the kind of issue that we're responding to, okay? And this is a proposal called Performative Power. It's with Mina and Celestine that just appeared on the archive, I think yesterday. It was no April Fool's joke, right? It's meant to be a serious paper, okay? So it's on the archive, you can look it up. And so the informal definition, I'm gonna make it formal in a second, is that performative power is the largest change to a population that a firm can cause with respect to a given set of actions. And we think of these actions typically as like models that have, predictive models that a platform can deploy. And I'm going to give you several examples. But I want to say right away that there's no need here for market definitions, firms, prices, equilibria, or anything like that, which would go into traditional frameworks for reasoning about power. It's just sort of directly about the causal power that a firm has over a population with respect to predictive models. Okay, and that's what we're going to try to measure. Yes, it's very different from traditional antitrust machinery. Okay, so you don't need like a baseline equilibrium. You don't need you don't even know which firms are involved in the market. You don't need prices or anything like that. You do need a population and a population definition, and you do need to sort of think about what your actions are. Okay, so let's go to the formal definition and then see what we can do with it. The formal definition goes like this. You fix a population of participants interacting with a firm. And what your units are, I'll call them U, sort of depends on what you're trying to do, where you're trying to like identify anti-competitive patterns. So, this could be Uber drivers, or it could be content creators on YouTube, or it could be, customers on restaurants on Yelp, right? It could be any number of things that you instantiate this definition with. And F is a set of actions the firm can take. Typically, we think of these as a set of predictive models that an algorithmic platform can deploy, okay? But it could be other actions, and sometimes we'll instantiate these differently. And I'm going to write ZU as the data of participant U, okay? So every participant U has a data vector that I call Z. And here's an important, construct. Let Z subscript F of U be a potential outcome representing the data of participant U if the firm were to take action F, okay? So the causal counterfactual potential outcome variable representing the data that would manifest had the firm taken action F, okay? And so, okay, are these ingredients clear? And so this potential outcome, these could be random variables, okay, in general, or the potential outcome could have a randomness in it. Because the Z is indexed by U, I can imagine that's just fixed vector, ref.
Could we have like a running example maybe?
Yes, absolutely. I'll instantiate this in a second. Let's just appreciate the formal definition and instantiate it, okay? So we define the performative power of a firm with respect to the population, action set, and potential outcomes as the supremum over all your actions of the expected distance between the data of participant U and the hypothetical data of participant U under the action F. Okay, so the distance here is just a metric over the space of data points. It doesn't have to be something fancy. It could be something like just an absolute value or something like that if you have a single feature that you're interested in. And the expectation is taken over the random participant U, a random draw participant, and the potential outcome randomness. Okay, so this is the abstract definition. And let me go into an example to see how to instantiate it. So again, this performative power, supremum over actions of a firm, expected distance in the current data and the counterfactual data that results from the action. Okay, so first you choose your population and units at one end of the power relationship. In my example, I'm going to choose restaurants in the United States. Okay, and I'm going to, as the platform, I'm going to choose Yelp. Okay, so this example is about Yelp. I'm going to choose Yelp. I'm going to choose restaurants in the United States as my population of interest. And I'm going to model actions, that are within reasonable agency of the firm. And I'm going to take this as the set of ranking models that Yelp could deploy. Okay, so these are all the things that, Yelp, all the scoring models that Yelp has and could deploy to rank, or to rate, restaurants. Okay, and finally, I have to pick this Z. And this is, you pick things that you think are salient to the power relationship and are sort of like reflect the well-being of the unit. Okay, so in this case, I take wait times of the restaurant. Okay, how much business the restaurant has. So it's kind of like a proxy for how much business the restaurant is getting. So I look at Yelp, I look at restaurants in the US, I look at the set of scores that Yelp could deploy, and I look at how busy restaurants are. Okay. Is that an example that sort of makes it clear?
So here in this model, you assume that Z exists without the firm. But for instance, for social media, you may need a action to have a feature.
Yeah. That's a good point. So think of this Z. You're asking why does the Z not have a subscript? Mm-hmm. Right. You could think of it as like kind of the baseline data point, which could, for instance, be the result of the current action that the firm plays. Okay. Right. So yeah, I mean, you could like introduce an extra subscript here, which is like the current baseline state of the world. Similar to how in performance prediction, you could imagine that you start out in some distribution and move to somewhere. This is kind of how you should think about this. That's good. Okay, so the Yelp example, I'm actually going to return to in a second. But for for now, I want to just convince you that this definition, or with a little bit of theory, that this definition is doing what it is supposed to do. Okay. Questions about this so far? Yeah.
Where do you get ZFU?
ZFU, yeah, it's a potential outcome variable. You may not necessarily be able to observe it, right? But one thing you can see, or like, you can in principle apply all sorts of causal inference tools to get this, an estimate of this, right? This is essentially like a treatment effect, right? Under this intervention of F. One thing you can do, for example, is suppose you have data before the firm deploys a model and data after a firm deploys a model. That would be one way of getting it. But we'll see more clever ways to estimate this in just a second. But conceptually, for now, you can think of it like having data before an intervention and after an intervention. Okay. That's how you get it. And you don't notice that you don't need it for every unit. You just need the average. Okay, like we're looking at the expected value here. So you don't necessarily, you just need to be able to estimate it from samples. Okay, you can't estimate it from samples. You don't have to know this for every unit. Does that make sense?
Yeah, it does seem to me that if you have that information, you could go back and get the market equilibrium or the prices or all the things that you said were too hard to get.
Oh no, I disagree, right? Because let's say I give you just like the wait times of like Yelp restaurants before and after I deploy the model. Now give me a market equilibrium. I don't see how.
So you're not modeling anything about the change in behavior, the behavior of the restaurant. You're just observing.
I'm just observing. Yeah. So no, from this alone, there's no way I could back out a market definition. I'm just really observing like data before and after some action. And the features could just be like one feature, like, the wait times at the restaurant or something like that.
Yeah, so maybe it's saying something obvious, but these market definitions are useful to the extent that an antitrust authority can actually operationalize them. And so here, an authority would never be able to run experiments. It doesn't have the data.
Oh, that's all. No, we first of all, two ways. Okay, do we have the data? We'll see in a second, like in many cases, yes, we can get lower bounds on this from like data we have. Second, especially if you're thinking about regulation, this gives you like a concrete thing to ask for, right? So yeah, you could operationalize this as like, let me run this experiment, right?
Right, that's kind of invasive. So if you could run an experiment on a platform, then it's like you could do many things. Because if I can,
No, I disagree. It's just an A/B test. Platforms run like 1 million A/B tests every day.
I see that, but I never seen an authority like asking a platform to run an A/B test. I mean, that's just not in the antitrust debate. It's too invasive.
Okay. So if you have that mindset, which I may not know enough about antitrust to sort of judge, but if you have that mindset, you can also estimate this from observational data that you have about platforms, and I'll get into that in just a moment.
Especially if you have the cooperation of the restaurants who might be the ones who are making the claim about antitrust.
Exactly. I think you can get that data in a lot of cases. I mean, I think if I ask Armin nicely, he would let me run this A/B experiment in Google. No. No. Okay, maybe. We'll talk about it after.
So you have a lot of market power.
So first of all, experiment, second observational. So just let me be clear what how this works is, right? This is a causal notion. There were 2 ways to go about it. One is experiment, and the other is like, observational causal inference, right? And both of these apply. If you can do an experiment, great. If you need observational causal inference, then we can talk about how to do that, and I will in just a second. Ali.
I don't understand why the definition is based on a single intervention or a single unit. I mean, why is it not based on set of concurrent interventions? Some restaurant that would be more popular than selecting the random.
Why is it the expectation? Are you asking?
Oh, no, I understand. Taking expectations, you still consider if I have intervened on a single random restaurant. What if I have intervened on 2 restaurants together?
Oh, no, this is like the intervention is on the platform. So this is Yelp deploying a new model, which simultaneously affects all restaurants. This is just like how that intervention affects unit U. Right. So like F is the intervention is sort of something the platform does. And then there's like an effect that intervention has on every unit. And that's this counterfactual variable.
I thought maybe it's the case that I'm using different models for different.
You could think about that. Maybe that corresponds to something interesting too. I haven't thought about it. Yeah, it's a good question. Okay, so here's a key property that this has, which is a theoretical property. And so basically low performative power implies that the best the firm can do is ex ante optimization on current data. And there's no gain from ex post optimization. Okay. So let me state this claim. Suppose we're in a world that is given by a baseline state theta 0. And this goes back to your question, right? So we're assuming there is some baseline state given by theta 0. Theta 0 is a model. And let's suppose we're a naive firm that's just doing supervised learning in current conditions. So we're just running supervised learning against current conditions. This is the theta supervised learning solution. And then suppose we're a sneaky firm that is doing a performative optimization and somehow gets like the performative optimum, theta PO, okay? Then I claim that the performative risk of the supervised learning solution is upper bounded by the performative risk of the performative optimum plus the performative power, okay? So in other words, if the performative power of the firm is low, you're essentially a price taker, okay? The market gives you current conditions and all you can do is optimize against it. There's no gain from like ex post steering, okay? There's like steering gives you nothing or very little, just something proportional to your performative power, okay? So basically what we're gonna see is that low performative power is a conceptual analog or alternative to competition, okay? So low performative power is kind of a proxy for competition. And just like in a competitive market, you become a price taker. Under low performative power, you essentially become an optimizer. The only thing you can do is supervised learning. Okay, there's nothing more clever you can do.
So the firm is, so maybe this is obvious, but is a firm trying to minimize their risk or are they trying to make money?
Very good. Yeah, this is an excellent question. I would go into more in detail. So basically, the way firms actually operate is they might solve some optimization problem and then they deploy, right, or do an A/B test to estimate profit, right? It's like very hard to like directly optimize profit in the advertising ecosystem, right? So basically you solve these, there's sort of this loop where you solve like an optimization objective, you deploy to see how much money you're actually making and so on, right? And so you could talk about being performative on the profit objective, right? And there's a very good observation here of like, Are you trying to be performative on the profit objective or on the supervised learning objective, right? And there's a difference, right? And so you're kind of hoping that by being performative on the optimization objective, you're performative on the profit objective. But just like there's a disconnect between optimization and profit without performativity, there's a possibly even bigger disconnect between optimization and profit in the performative setting. And you can think about when they disconnect. That's a great question, Raph. Good. Let's move on. And this holds in generality. This is just like a general property of performative power. There's a whole lot you can say if you're willing to introduce micro assumptions, right? And so you can now play this game where you say, let's actually see what this definition does in sort of more concrete market settings and see if it does the right thing. So this is something I encourage you to do. Pick your favorite market setting. You look at performative power, see if it sort of does the thing you expected or wanted to do. So we did this with strategic classification, where we make these standard assumptions and we see how performative power plays out here. And so the first thing we observed is that a monopoly firm maximizes performative power. Okay, so if you just have a single firm in your setup, a single predictor, then participants are willing to incur a cost equal to the utility for the service. So they're willing to pay the full price for the thing, at which point they basically have like no net utility for the service because they expended everything on like adjusting to your model, okay? The moment you introduce outside options, meaning there exist firms that give you some utility elsewhere, you're not willing to pay the full price. And so, performative power decreases proportionally to how attractive your outside options are. The more attractive the outside options, the less performative power you have. Third, when platforms actively compete over users and users can switch between firms, and these firms offer services that are substitutes. So let's say you're a content creator and Twitch and YouTube are equivalent for you, you don't care between them, then even two firms give you zero performative power. The existence of two competing firms with perfect substitutes give you zero performative power. What does that remind you of? Who remembers Micro 101?
I don't know, perfect competition.
Yeah, Bertrand competition. That's exactly right.
Yes.
Yeah. So okay, maybe too easy for this audience. Okay, I'm.
No.
Okay.
Just a quick comment. It
Yeah.
seems that you were assuming that there is kind of a wedge between the firm's incentive and the consumer incentives. I mean, it could be the case that if I have power, I use it in a way that increases surplus, makes customers happy. So where is that assumption here? I don't see it formally, but
Yeah. So very good point. This gets at another fundamental point that comes up with all measures of power. There's a difference between power and like harm, right?
exactly.
Like, you could be like highly performative because you somehow were disruptive. You just had a better product.
Right, exactly. Yeah.
And so like with all measures of power, there's like they're a step removed from like arguing about harm to the consumer, right? So, and that's where, the features are relevant, right? Like the features determine whether or not they reflect harm, right? And so, yeah, I mean, a firm could be performative in a way that doesn't harm the consumer. It's a very good observation. Okay, yeah, so this is analogous with a Bertrand competition where like two firms simultaneously set prices. And if you set a price that was a little bit too high, like all the users go to the other, or all the consumers go to the other firm and you get nothing. Okay, you have the same phenomenon in performative prediction where you get zero performative power if there are two competing firms. Okay, so these are like just some theoretical properties to like convince you that this is a reasonable definition or suggest, but I would love to see more work on this, yeah.
I'm really curious to understand the performative power and the epsilon sensitivity you had in that model that we had. Like, because when you said you were going to define performative power, I just thought you were going to talk about the epsilon factor.
Oh, interesting. Yeah. So does the epsilon sensitivity give you bound and performative power? That's sort of what you're asking.
Yeah, exactly.
If you assume you start out from a state, right? You're currently in a distribution that's given by one of the model parameters. Then your performative power, and you're within some L2 ball, right? Let's say of radius B, and you're epsilon sensitive, then I think your performative power is bounded by epsilon. Does that sound right?
Okay.
Yeah. So that's the point we would get. But yeah, we don't. We've moved away from the epsilon sensitive in this thing.
So then, if you can predict, so you said that you get actually a prediction of what your performative power will be. Does that also mean that you can actually have an idea of what your distribution will be? And Like you can learn the distribution and these hypothetical scenarios when you're like implementing.
Oh, this is fascinating. So you're saying assume low performance power, does the retraining converge?
Exactly, yeah.
Ah, interesting. Yeah, I have to think about it for a little bit. If you set up your distance function, so that it gives you, basically one way to get that is if you set up your distance function, give you the Wasserstein metric,
Yeah.
and use in low performance power, then it gives you like epsilon sensitivity, and then you would get that result, right? Does that sound?
Yeah.
Yeah, it's a little different because it's a Lipschitz condition versus a soup, but
But if you assume that like basically you have a ball, right, and like you're at the center, and then the soup gives you like up to a factor 2, like basically the whole thing, right? I think something like that could work, but it's interesting. Maybe this is like an alternative to the epsilon sensitive. You assume low performance power and then actually retraining converges.
Yeah.
That would be a very nice result, actually. Yeah. Okay, cool. So since this has been burning on everyone's mind, how do we estimate this using causal inference? So how do we go from causal effects to performative power? I'm going to return to the Yelp example. And I look up a paper by economists Anderson and Magruder from 2012, where they did some regression discontinuity, and they argued that an extra half-star rating causes restaurants to sell out 19 percentage points more frequently, so almost 50% more for just a single half star. So if you somehow had like 4 stars instead of like 3.5 stars, you would get massively more business. How does that relate to performative power? I argue that any such like causal effect that our econ friends have been surfacing, of which there are many, actually leads to a lower bound of performative power using like a nice trick. Okay, so remember, we're looking at the sort of supremum over possible actions of the distance in these counterfactual variables. And so what you can do is you can take this action F to be Yelp's action that perturbs the score around the the star thresholds. So like people who are just on like 3.5, you like perturb it a little bit. And you take ZU to be the restaurants, what you're interested in, like wait time or number of customers, whatever you're interested, like your measure of welfare for the restaurant. And then you can see, you plug that in and you can basically repurpose this causal effect that they have as a lower bound on performance power. So you can say that, your performance power is at least as large as, the effect of a single half-star rating. Purely observational. And in fact, you just look at a paper and repurpose the findings of the paper. You don't even really need to rerun anything. So this is like an observational design. Okay, you can generalize this, and this is what we call the display discontinuity design. And it's based on this observation that online platforms display scores discretely. Okay, so most platforms have some way of discretizing their scores. Stars, but also ranking positions are really powerful. Positioning is really powerful. Ordering is really powerful. Coloring is really powerful, like Rotten Tomatoes, red or green. Right. So you can think about your favorite recommender system. You'll see that it has ways of discretizing information. And any causal effect of such display discontinuities can be converted into a lower bound of performative power. So whenever somebody went through the effort of like, let's say, determining the effect of like, tweet ranking on Twitter, right? Like how much does it help you to be like the #1 tweet on the timeline versus the #2 tweet? Or somebody has determined how much of an effect is there on YouTube for the first, video on the upper left versus the, last video on the lower right. All of these are display discontinuities. Suppose somebody bothered to like experimentally or otherwise figure out the causal effect of display discontinuities. You can convert that into performance power estimates. Okay. And the idea is just to take the platform's action so as to swap items around the discontinuity. Okay, since I'm out of time, let me wrap up. This is my last slide, and then we can see if there are some more questions, or I'll take it offline. So classical antitrust tools need market definitions with specific kinds of competition wired in. They might need equilibrium notions. They might need specific dynamics or assumptions about firm behavior or user behavior, customer behavior. And what performative power does instead is it needs a population definition. Okay, if you're the investigator, you need to put your finger on the population where you expect the power relationship to manifest. Okay, so you as the investigator specify units and features where you suspect the power relationship to become visible. Okay, and that's like an important step of the investigation. It's not sort of like an abstract thing you can resolve. That's like context specific. And the interpretation of the features that you choose determines whether or not the power is harmful or how much power you measure, okay? So this is not entirely plug and play. You need to think carefully about how to instantiate this. Okay, but the interesting thing here is that sort of low performative power is a conceptual alternative to competition. Okay, you can like sort of try to lower bound performative power various ways. And if you kind of fail to like lower bound performative power, that gives you like a sense that there's competition happening in some way or another. Either people have outside options, or they have alternatives, or there's actively user switching and whatnot. Okay, so this is the way this logic goes. Again, I think it could be a helpful complement to some of the existing tools. All right, that's it. Thank you.
This is really interesting stuff. I had a question about like if you think about, so the policymakers is policy, the population response, and then in some sense like the policymaker kind of responds to that. Can you think about like a dual version of performative power where instead, I don't know how to write this exactly, I was trying, but maybe the soup is over the distributions, and then instead of having like an F on the inside, it's like F sub distribution. Is that something that's worthwhile to think about? Especially if like, maybe Uber drivers like, are working together to respond to a pricing policy of Uber.
No, exactly right. So excellent question. So yeah, two things. I mean, first of all, this reminds me of a paper Tiana co-authored on like where you switch the order of like who goes first, right? And you can think about that as sort of has a slightly different interpretation in terms of power, right? Like users or consumers going first sort of says they're in charge, right? And so you can imagine like if people, let's say, do collective action and they, form a union or whatever, then they might go first. And yeah, we've been thinking about these things in the context of collective action, where like if all the users got together and said, we're the restaurants and Yelp is messing with us, so how should we coordinate our move? And then you might get like a very different dynamic, and that's an interesting direction. Happy to chat more.
I have a question. Sorry. I have a question regarding the observation you had from Yelp. I think the observation was if you increase the rating of a restaurant by half a star, given all other restaurants are the same, I think you can increase the purchase, I don't know, of that restaurant, something like that. Mm-hmm. Is that correct? I mean, you assume that all other restaurants are doing same and you increase a single restaurant rating?
I see what you're saying. So you're saying like, the causal effect was sort of meant to be unilaterally, right? Like if you leave like star distributions
exactly, and this will be expectation of maximum, not maximum of expectation.
So you need to be a little bit careful, right? So this is a good point, right? So let's say you increase everyone's rating by a star, right? Then somehow like the distribution just moved upwards, right? So you need to be a little bit careful about how you do it. So that like,
so my question is, how do you relate these unilateral changes to performative power? How do you lower bound with these observations?
How do you lower bound with this observation?
Yeah. I mean, we have some unilateral causal effects, and you say that you can lower bound this performative power with these observations, but to me, it's not clear how do you use them, because in performative power, in the calculation of performative power, we need something general, not unilateral, maybe.
Yeah, so I see your point, and it's a very good point. So let's just repeat the point. So you're saying in performative power, you're doing an intervention, it affects all units. So it's sort of like it might have an effect on all the units. In this regression discontinuity that they did, they're interested like sort of the effect they're interested in is like if you increased like a single restaurant's rating by half star, you get this effect. Yes, so you need to be, if you instantiate this, you need to be careful that you're not like inflating, the score distribution, right? So you need to somehow keep that fixed. And so basically one way you can do this is by just swapping restaurants, for instance, around the threshold. And then you're just like moving business from one restaurant to another.
Oh, hi. I have a question. Have you heard of these inference on counterfactual distributions? It's this idea of estimating a policy effect like the marginal, the effect is the change on the marginal distribution of outcomes, but you consider a fixed distribution on the covariate density. So in relation to that, this kind of sounds like a data-driven setting where the outcome is the change in the covariate distribution, but presumably these could be combined, perhaps, like the distribution on the features, as well as the counterfactual distribution on the impacts on the marginal distribution of outcomes, like wages, for example.
Yeah. I mean, that sounds very interesting. I would love to hear more. I mean, like I said, there are all sorts of causal designs that could be helpful here. This sounds like one that is relevant. So would be happy to figure out how that can be used here.
Yeah. Just a quick clarifying question on the running example. So in that example, you have two kind of endogenous choices. So one is restaurants, they adjust their standards quality to the rating system. And the other one is that consumers, they have to figure out how to interpret those ratings. So if you try to pretend that a 1-star restaurant is a 5-star restaurant, consumers, right, will figure that out. Right. So the effect will be different.
Absolutely, yeah. So I think, you know,
are you capturing both with this notion, or?
So basically what you would have to do is, what you do is like you swap restaurants just around the threshold, and you assume that, you know, restaurants that were scored almost just like the same have like similar quality. So the only thing that changes is the rating, the half-star rating. It wouldn't work if you like swapped like a 5-star with a 1-star.
That I understand, and I knew that paper. Right. But then, you know, when you're thinking about power of the firm, you know, where is this captured? Like you can do things at the threshold, but not too much, because otherwise customers will figure out. Formally, are you capturing this disciplining force?
Again, like you would need the same assumptions that you need for the regression discontinuity. When you design your action F, you need to make sure that you satisfy the assumptions of the design. So that's what's going on. Good question.
I think this question is where I got confused before, because I went with the ZFU question, because I was thinking that was somehow modeling the behavior of the restaurants, but I guess it wasn't modeling the behavior of the restaurants, it was modeling the behavior of the consumers or the restaurant goers. So the behavior of the restaurants is not at all part of your model, or somehow?
So yeah, this is an interesting question. So when you introduce these counterfactual variables, right, you're just saying there is some kind of causal effect from my action to the features. The mechanism is, you know, could be anything, right? The mechanism could be something that involves the restaurant's behavior, or it could be something that involves the consumers.
The F reviews could include, for example, like the data that the restaurants provide together, right? And you could look at the changes that happen based on like what F was.
Yeah. So that basically the taxonomy of performativity in these like recommender systems is a little bit more complex than just this example, right? There are a lot of things you could influence. You could sort of like influence what's on your platform. You can influence what's, you know, consumed on your platform. So there are different mechanisms that determine performativity. And so, you know, it's a little bit like in a grocery store, right? So you walk in, the grocery store can rearrange the items, right? To like steer consumers in a particular direction. Or they could price items differently so that suppliers either provide something or don't, right? So you can kind of change the supply side or the consumption side. And which of these mechanisms that at play depends on what features you look at and what your action is, right? But it doesn't need the mechanism. You don't have to like model the mechanism to, you know, formally introduce these counterfactual variables and maybe, you know, estimate them from experiment. But if you wanted to reason about it theoretically, yeah, then, you know, some such model might be helpful. So like we did in strategic classification, there we actually model what, you know, the behavior is, right? So yeah, for the theory, like if you want to prove stronger results about this, you might need a model. And maybe, you know, you'll even introduce a whole sort of like market model, right? And then it's like, you could also evaluate other notions in that model. Right?
I think then you get back to the question I had at the beginning about, you know, distribution changing in response to,
right.
Yeah, as you talked about classification. Come back to that. You never got to the equilibrium between the D and the theta.
That's what I meant, is just in these strategic classification setting, the equilibrium is a Stackelberg equilibrium. That's the sort of natural equilibrium in that setting. And I had a suspicion that that's what you were getting at, but maybe not. Okay. We're happy to
I had in mind like the Coates and Lowry model when I
Yeah, no, definitely happy to chat more to clarify. Yeah.
This is also a zero view question in the sense like, so we're defining this power, I forgot, the performative power, right? So we're thinking about, we want to know how this institution, this entity is able to change the distribution, right? So there is so much in this choice of Z, right? And I think there is a tension here, like when in the example you showed for the Yelp thing, I think the example of the Z of you was like the waiting times on the restaurants, right? So I feel that this is also very likely of being a feature of the model, because there's like, those are concurrent problems, right? Because people choose the features because they think the features are describing the problem well. So in real settings, they're probably gonna be using all the information they have. So there is a tension here, and I'd like to know your opinion about like how to reason about that. If you want to, I mean, if you're trying to be careful in causing all of that.
Yeah, no, so I think you make a good point that the features that you look at, the Z's, are probably also something that went into the optimization of the platform previously, but that's not necessarily, I don't see the tension, it's just something that can happen. But yeah, let's say the wait times of restaurants yesterday influenced my scores. And I'm looking at, the wait times under some hypothetical action. So you're right, the observation is correct. I just don't see the tension. So maybe we'll discuss that a little bit more. Cool. We should give people a break.
Yes, I think that's it. Thank you so much again.